Hello, everyone. My name is Minić from Seton University, and you already met Oliwia from University of Maryland. Today, we're going to show you how we visualize composed Turing machines in FSM. This is joint work with our advisor, Morazán from Seton University. So I can imagine that a lot of you taught Automata Theory class or took it in college, and you all know that it's very common for students to struggle to design Turing machines using pencil and paper. This is mostly because of the low levels of abstraction that they encounter, with basically no interacting, testing, or any debugging available to them. So to aid students, we developed FSM, a domain-specific language embedded in Racket, in which they can design, implement, and test state machines, regular expressions, grammars, and Turing machines. So there is, even though FSM helps them design Turing machines and program them, still when they encounter more complex problems, it's still hard to deal with those low levels of abstraction. So to aid that, we teach them how to compose Turing machines. So they're basically treating a Turing machine as an auxiliary function to solve a bigger problem. So this helps them break that problem into smaller sections, design Turing machines for smaller parts of the problems, and then just compose them to solve a bigger one. However, with everything provided with FSM and composing Turing machines, students still find it hard to design them. So to aid them, we wanted to, actually, it's very difficult for them to mentally keep track of the sequence of executions. Sorry, this pointer is like delayed. So it's mentally hard for them to keep track of the sequence of the executions in the composed Turing machines. And it's also hard for them, once they have an input word in mind, to kind of mentally trace it throughout the composed Turing machine. So we don't want them to go back to pencil and paper and still kind of resolve to drawing everything out. So we wanted to provide them with visualization tools. So we developed two new FSM visualization tools, a static tool that returns them the transition diagram of the composed Turing machines they've designed, and a dynamic tool that provides them with a stepwise execution of a composed Turing machine on an input word.
Right, now, brief introduction to FSM. I know you already saw this in the last talk, but for any newcomers, and just as a quick reminder, to implement a Turing machine, use the constructor makeTM. Takes as input a list of states, alphabet, transition relation, a start state, and a list of final states, and an optional argument y. If that's provided, it's a language recognizer. Okay, now let's see what it looks like to implement a Turing machine. So that's actually different from an NDFA. The student first comes up with a pre and post condition. Here we're going to design a machine that is supposed to move the head on the tape one position to the right. The precondition is that the tape starts with a left-in marker, which also can be visualized as an @ sign in the graph. And then it's followed by the actual input word. Okay. A left-in marker is supposed to prevent the head on the tape from moving left over the start of the tape. On the right, you can imagine an infinite number of blanks. So whenever the head moves right over the tape, there's going to be a blank, which also looks like an underscore in the graph. And this is what the tape is supposed to be like as a precondition. I is the head position on the tape. It's supposed to be greater than 0, because 0 is where the left-in marker is. Sorry. Now the post condition is that the tape remains unchanged, but I increments by 1, effectively moving 1 position to the right. This is the implementation of the machine. On the right is the transition diagram. The green state is the start state, the double circle is the final state. A transition for a Turing machine consists of 2 parts, the red element and an action. An action can be to move the head right on the tape, to move it left, or to right to the tape. Essentially here, regardless whether an A, a B, or a blank is being read, the head just moves 1 position to the right, the machine transitions from start to final state and halts. And that's the move right Turing machine. Now, if the student has a bunch of Turing machines like this one, they can combine them all together into one big composed Turing machine. This is the description of it. It's a list, and it can either be empty, it can contain a machine, which is another Turing machine, or another composed Turing machine. It can contain a label, which is an integer, and a go-to statement that points towards a label. Then it can contain a branch. A branch is a list of lists. Each of these sublists consists of 2 parts, the read element and a go-to statement. Essentially, whatever is being currently read on the tape is the branch that's being executed. Then it can contain a variable declaration. Once a variable is declared, it can be written to the tape, which is number 7. Now we'll see an example of this. We'll use a copy CTM. The objective is to copy an input word on the tape. The precondition is that the tape starts with a left-hand marker, followed by a blank, followed by the actual input word that we want to copy, and it also ends with a blank. The head is on the blank after the word. The first thing this machine does is it moves ahead of the word. It finds the first blank to the left. Then it moves right into the word and copies the first element over. It repeats that for every element of W until it reaches the blank after the word. And then all that's left to do is readjust the head position and the post condition becomes true, which is that the word is copied on the tape and that the head is on the blank after the second W. And now we'll see a demo of this in code. All right, this is a little small. Is this large enough? Yeah. All right.
Bigger?
Bigger.
I think it's going to fit. You can, yeah, there we go.
Yes?
Mm-hmm.
All right. And this is what it looks like to implement a composed Turing machine. We have our pre and post condition clarified. We define copy and use combined TMs. Combined TMs takes as input 2 lists. The first one is the description. The second one is the alphabet, in this case A and B. Right. Now the start of the list is FBL. It's a composed Turing machine that finds the first blank to the left, moving the head of the tape ahead of the word. Then we have 0, the first label. There's 5 of these. 5 labels that split up this composed Turing machine into 5 parts. Everything that follows the 0 label has the objective to check whether there's anything left to copy. There's a branch, and if an A or B is read that needs to be copied, the machine goes to label 1. Here, whatever is currently being read, A or B, is being declared as a variable, and it's being copied over. And the machine returns to 0 to repeat that for every element of the word until it reaches a blank. In that case, it goes to 2. Now, the objective of everything that follows label 2 is to check whether a word has been copied or whether maybe the word has been empty from the start, because in that case, the head position needs to be readjusted differently. Once that is being checked, the head position is readjusted after label 3 and 4, and then the machine jumps to 5 and halts. Right. So this is the copy CTM in code. Now, it's still pretty difficult to visualize this, even if we see this code, because there's jumps, there's all these machines, there's variable declarations. It's almost akin to assembly code, which is what motivated our first tool, the static tool that returns the transition diagram. So this function takes as input the description of the CTM and returns the transition diagram. Nodes denote machines, and transitions denote the sequence of the execution of the machines. A green rectangular node denotes the first machine to be executed, in this case FBL. Once the first blank to the left is being found, the machine moves right, which is the R machine that we've also seen before. Now this is a diamond node, and it's golden, which means it precedes a branch. There's also dashed edges that make this even more clear. Depending on whether an A or B or a blank is being read, that's the branch that's being executed next. Let's say on the tape, there's currently an A. K is being declared as A, and then whenever K is being executed, that A is being written to the tape. Now once a blank is being read, or if maybe the word has been empty from the start, the machine takes the top branch. Here it moves left again just to check whether this word has been empty or whether it has not been empty, and then it readjusts the head position accordingly, either 1 or 2 steps to the right. And this is the static tool.
Now, you might have noticed while Oliwia was doing the demo of the static tool that while it visualizes the sequence of executions, she still has to tell you where the word would move in the tool. And as you might have also noticed, there is no tape. So she's telling you what's happening on the tape, but you can't see it. So to help students with that, we decided to develop a dynamic tool that actually walks them through the execution of the composed Turing machine on a given input word. So our dynamic tool takes as input the machine, the description, the input word, and the initial head position, so from the precondition. And once we run it, this is what the dynamic visualization tool looks like. So you can already see that we have the transition diagram that Oliwia just showed, but we also have the tape with the initial head position highlighted in red, so we can track where it's moving. We also have a list of instructions that the students can interact with by pressing on them with the mouse or interacting with the corresponding keys of the keyboard. Now, if I want to start executing this composed Turing machine, I can, well, I'm going to do it on the pointer, but I can press the forward button, and it's going to execute the FPL, which we can see because it is bolded now. And we can see that this edge is now highlighted in blue, and it's pointing to the next machine to be executed. You might have noticed that the initial head position has now moved to the first blank to the left, because now this 0th position on the tape is highlighted. So we can keep executing. We're going to move one position to the right on the tape, and now because we were on a branch and read an A, we go down here and we've declared K to be A. We can keep moving and executing these machines, and now an interesting case is going to come here once we write A to the tape, because we declared K to be an A and now we are writing it to the tape. We can keep executing the word step by step, or we can complete it in one step by clicking the finish button. What this will do is it's going to jump to the last machine that was executed, which is this R in the case of this word, and we're still going to have some sort of idea what the last machine executed was, because it's going to be bolded, and we're also going to get a message saying that the composed Turing machine halts. We can see that the entire word is now copied on the tape, and in case, for example, the word is too large, and if the copied word goes over the visible part of the tape, you can use these two buttons to move through the tape by one index. So you have access to viewing the entire input word in case it doesn't fit. If any students want to more closely observe any parts of the transition diagram, they can use the zooming capabilities or the dragging by executing any of those buttons. Or if they just want to restart the entire thing, they can just start over and execute the machine again. So this way they have access to any part of the transformation very quickly. The goal of this tool was for it to have low extraneous cognitive load. We didn't want students to waste too much time just learning how to use this tool, or even waste time trying to arrange these nodes so they can look appealing. We wanted them to focus all of that time on the actual process of learning. So this is our tool, and I'm gonna give you this. Okay.
5 minutes, all right.
No problem.
So essentially, we also have some related work. JFLab is also a system that lets people sort of work with composed Turing machines. They call it Turing machines with building blocks. We call it composed Turing machines, and for us, it's Graphis that generates the transition diagram. The user does not need to create it by hand. Now, this is kind of an important distinction because we tried to implement the copy machine in JFLab. This is what it looks like, and we run into some difficulties, namely 3. 1, you have to drag around every node, which with every change you make is really maddening, especially if you're a perfectionist that really wants us to look perfect. So 2, in JFLab, the machine can't really transition from one node to the next without on just any input. You have to specify which input it is. So if it's just any input, you have to over and over create all these labels for every single transition. If you wanted the whole alphabet to be able to copy, that's 26 letters. You'd need 26 labels that you have to do manually. And then finally, there's no variable abstraction in JFLab. So you might have noticed already there's 2 of these loops, one for B, one to copy an A. If you had 26 letters, you'd need 26 of these loops, which is not really feasible. And FSM lets the user work with more complex mechanisms.
And you don't have to organize 26 loops on your screen, which is really nice. So to assess the effectiveness of the tool, we conducted an empirical study at Seton Hall. We had 10 volunteers, 7 male and 3 female, and they were all taking their first flat course in their junior or senior year. So we asked them questions about the dynamic visualization only because it already contains the transition diagram, so if we could gather feedback on both. And they answered on a Likert scale from 1, strongly disagree, to 5, strongly agree. So we asked them 2 kinds of questions. So this first group of questions was assessing that low extraneous cognitive load. We wanted to see if the tool was clear to use. So we asked them whether visualizing the execution of composed Turing machines using CTM-Viz is clear, whether using CTM-Viz to visualize the execution of CTMs is straightforward, and whether they would recommend to someone using CTM-Viz to design and debug. machines. So you can see that the results are overwhelmingly positive. Over 70% of the students answered 4 or 5 for all 3 questions, which to us suggests that the tool has low extraneous cognitive load. And the second group of question was more concerned with the actual usefulness of the tool. So we asked them whether the tool is useful, whether it's used for debugging and for design. And we can see that the results were also very positive. Over 70% of the students said 4 or 5 for the first 2 questions, and over 80% of the students said, over 80% of the students said 4 or 5 for all 3 questions. In conclusion, we give you a novel graphical approach to help students understand composed Turing machines. It is already integrated into FSM, and students can use it. It contains low extraneous cognitive load, and our future work includes the generation of transition diagrams for multi-tape Turing machines and visualization tools for different grammars deriving words, which we also presented at a poster yesterday at Student Research Competition. Now, we already mentioned this, but if you want to learn more about programming in FSM or deploy our approach in your classroom, this book, Programming-Based Formal Languages in Automata Theory, written by Marco, is available at Springer. And thank you so much for your attention. We are open for any questions.
Yeah, there are 3 questions. I don't think we will have time for the 3 of them, so.
This is really cool. This works basically like a macro assembler and a debugger. I'm just wondering if you have implemented the step in, step out, like you have this Turing machine and then you can step in through it and see those small steps, right? So right now, when you step through, a macro step, it just goes over it, right, fully. Are you envisioning drilling down into the execution of a single one, a level?
We're discussing that.
That could be next step. That's really interesting.
Yeah, we were discussing that before, and
Because you're right. Right now, if it's a big composed Turing machine, it looks the same as a small Turing machine, so it's just being executed all at once. But it would be nice to sort of have something.
Our plan was to click on the machine and then display like the micro steps of that machine, but that's in the works. Yeah.
You can check out, Java debugger does it.
Thank you.
So in normal programming, people often reach for printf over debuggers because it unrolls program state over time. And I'm curious for your system, if you get the sense of both watching students, do you think it would be valuable to have a version of the tool that can show sort of multiple changes in program state over time? And if so, what would that look like? Have you put some thought into how you could think about that instead of just the sort of single state model that currently exists?
So we have SM show transitions for every kind of state machine. So for Turing machines, for NDFAs, DFAs, you can do SM show transitions on the machine that you've designed and an input word, and it shows you where it is in the machine.
We just found that it wasn't enough to just see text. So
we don't like text for some reason.
So we also added pictures, essentially.
Yeah.
Really cool work. Definitely one place where I really like the dynamic over the static. Did you collect any other metrics during your user study other than Likert scale questions?
So no, we don't have, our class, as you might have noticed, at Seton Hall is pretty small, so it would be unfair to give them a control group study. For example, 5 students get to use the tool and 5 don't. And what we do now is, because FSM is being used in also Worcester, we are trying to do like an end of the year study where we collect as much possible data from students, just about the experience using the tool. What we were planning on doing with our tools at Seton Hall was first do the exercises, then introduce the tool to all students, so it's kind of fair. So assess how they do without the tool, and then later on when we introduce the tool, see if their results have improved.
All right, thank you again.